Hello everyone, welcome to this presentation. Today I'm going to talk about our work on formal policy synthesis for continuous state systems using reinforcement learning. My name is Sadegh Soudjani, and this is a joint work with Milad Kazemi from the School of Computing at Newcastle University. So today we use systems in many application domains that are large scale. They are composed of many interacting components with complex interactions, and usually the requirements on these systems are relatively complex. Think of application domains including transportation networks, power and energy systems, or robotics. So there are three features common between these application domains, which I will be focusing on during this presentation. One of the features is that usually these systems have continuous variables. The variables like speed, position, these kind of variables, they change continuously over time, and they can take any real values. These systems are usually operating in an uncertain environment. So there are lots of uncertain factors affecting the behavior of the system. And usually we don't have a precise model of the system. Because they are large scale, it's very expensive to construct precise models. Even if we construct those models, it will be difficult to analyze the model. Okay, so with this introduction, I will give the outline of the presentation. First, I will define the problem statement with some preliminaries. Then I will discuss how the problem can be solved. I will provide some implementation results with conclusion and future directions. Okay, so let's start with the objective. Imagine that you have a system. This system is influenced by the input, so you can apply a sequence of inputs, U0, U1, U2, and so on, and then you can see the state of the system changing over time. You get a sequence of states, S0, S1, S2, and so on. To specify the requirements on the system, we usually use a labeling function which maps the sequence of states to a sequence of labels, and then there is a specification that can decide whether the requirements is satisfied given this sequence of labels. So the answer of the satisfaction is either yes or no, depending on this sequence of labels. Now here I would like to bring your attention to the effect of uncertainty. So when we apply the inputs to the system M, the state of the system is influenced by the uncertainty. Here is denoted by W0, W1, W2, and so on. So then the answer, this yes-no answer here, depends on the uncertainty affecting the system and also the sequence of inputs. So if the uncertainty is coming from some probability distribution, we also get a probability distribution on the answer. So we may get the answer yes with some probability and the answer no with the complement of that probability. So we should talk about probability of satisfaction when we have uncertainty in the system. At the same time, this answer, this yes-no answer, depends on the sequence of inputs. That's why we're talking about policy. So the policy observes the state of the system and decides which input is better to be applied to the system. So here the objective is to find a policy in order to maximize the probability of satisfying the specification. So we're looking for a policy, but we don't know the model of the system. But we can generate input state data. So we can apply a sequence of inputs, observe the state of the system, and then try to find the best policy for satisfying the specification. So here is the objective. Given a black box model of the system, the specification and a labeling function, we want to find a policy that maximizes the probability that the system satisfies a given specification size. Okay, to give you an example of what kind of systems we are talking about here, you can see a cart pole system. If we use Newton's law, we can write down the evolution of such the behavior of such a cart pole system as a difference equation. So the next state of the system is a function of the current state, the input, the force applied to the cart, and also the noise, the uncertainty affecting its behavior. So for the states, we need a position of the cart, velocity, the angle of the pole, and also the angular velocity of the pole. So the state space here is the four-dimensional Euclidean domain. And in terms of the specification, we can talk about safety. We may want the cart to always remain within a range. We may want to always keep the pole upright. We may want the cart to reach some region, or maybe we may want it to visit some region infinitely often. Let's see what kind of framework is best for analyzing such systems. We can use discrete time Markov processes, which has a continuous state space S, some input space U, and a transition kernel. And this transition kernel gives the probability distribution over the next state, conditioned on knowing the current state and the current input. So if the system is at the state S, and we apply some input to the system, the next state is selected according to some probability distribution. And these Markov processes are very similar in nature to Markov chains and Markov decision processes, where you have a finite state space and probability from one state to another one. So here you can see three states, A, B, C, and these are all probabilities of jumping between these states. And these probabilities are gathered into a transition probability matrix here. But when we have a continuous domain, instead of working with probability matrices, we work with transition kernels over continuous domains. So we assume that the underlying model follows a transition kernel, but we don't know this transition kernel. For the class of specifications, we consider linear temporal logic. I don't give the formal definition for syntax and semantics, but I just give some examples. For example, you may have safety specification. You want your system to be safe. You may have reachability specification denoted by this diamond psi here. You may want something to happen in the system infinitely often. You may eventually satisfy something, and after some point you may want that property holds forever. You may also have the Boolean combination of these specifications. The example I just described related to the cart pole, you may denote the specification using this formula, but usually the specification, the requirements is written down using words to specify what we expect. Okay, so if you look at the literature, there is a large body of papers on how to verify LTL specifications on finite state models, including deterministic and stochastic systems. And we usually use automaton. We translate the specification to some proper type of automaton, and then we verify the specification using the automaton. So it is known that non-deterministic automata are not suitable for probabilistic systems. And if we want to use deterministic automata, we need to have a kind of complex accepting condition for the automaton, for example, the Rabin acceptance condition, which is difficult to use for continuous space systems. Here in this paper, we used recent results on limit deterministic Buki automata. So here, this class of automata is relatively simpler because the accepting condition is simpler. We want to take some of the transitions infinitely often, and the automata appears only in the first part of the non-determinism appears only in the first part of the automata. When you pass that first part of the automata, you reach to the deterministic part, and all the accepting transitions are in that part. Okay, and here there are some references, recent development on proving that this type of automata is suitable for probabilistic systems, and the non-determinism can help us on satisfying the specification. Okay, just to remind you the objective that we want to maximize the probability of satisfaction, but using data. If we look at the learning community, usually people use reinforcement learning, but they can only handle additive rewards. In the right-hand side, you can see a high-level view of reinforcement learning that you apply the input to the system, you observe the state of the system, and based on this input and state, you update the value function and the policy. So you start from some guess of the policy, some initialization of the policy, and depending on the data that you obtain from the system, you update the policy accordingly. And whenever you observe a pair of input and a state, you collect some reward, and the reward is additive. It means that it's summation of all the individual rewards collected in each transition of the system. And the value function holds some kind of estimation of the total reward that is updated, and eventually it converges to the optimal solution. And as I said here, the challenge is that the reward is additive, but our reward is not additive. So we want to maximize probability of satisfaction. This doesn't have an additive structure. Here the approach is to approximate such a problem with another problem that has a kind of additive structure. So we approximate the satisfaction probability with reachability. We cast reachability as an objective function with additive reward. So we put 0 on everywhere in the state space, but we add 1 to the target state, so that to encourage the learning to visit to reach to the target state. And then we apply model-free reinforcement learning. So this idea has been used in the literature, but only for finite state systems. But here we show that the same technique can be applied for continuous space systems, and we have convergence guarantee under suitable assumption. Another approach is proposed in the literature for continuous space systems without providing any convergence guarantee by Hassenbeck. So these are all recent development in this research area. Okay, so now let's see how we can approximate the satisfaction probability with reachability. So we add a sync state to the automaton, and whenever the system takes an accepting transition, it will jump to the sync state with some positive probability, 1 minus zeta. So zeta is a parameter that I will discuss later on, but here we fix the value of zeta to be, for example, 0.99, and then we compute the reachability probability to the sync state. To provide a theoretical guarantee, we need an assumption on the system that the expected number of times the accepting transitions are visited is bounded. If this assumption holds, we can provide the convergence guarantee. And we know that the assumption holds for finite state systems, but for infinite and uncountable state spaces, we have to raise the assumption. And here is what we get if the assumption holds. We get an upper bound, which says that the reachability probability is an upper bound for the satisfaction probability we are looking for. We also get a lower bound, but the lower bounds depends on the expectation of this quantity, the number of this tau in the assumption. So the upper bound always holds, but the lower bound, we need to know that this expectation is bounded. So this is good for having the convergence guarantee. When zeta goes to 1, this term goes to 0, and the reachability probability converges to the satisfaction probability. But if this assumption does not hold, we can still use the upper bound to also get a lower bound if we use the negation of the specification. So instead of trying to maximize the reachability, we take the negation of the specification and we try to minimize satisfaction of the reachability associated to the negation of the specification. And this gives us a guaranteed lower bound regardless of this assumption being true or not. Okay, so another point that we observed was that the learning takes a substantial amount of time to converge. And this is exactly because of the small number of cases when the pass reaches the sync state, when zeta is very close to 1. And then the chance that the pass visits the sync state is very small, or the specification at the same time might be very complex and it may be composed of contradicting tasks. So our idea was to modify the specification. To be more precise, we keep the structure of the specification to be the same, but we modify the labeling function to construct a relaxed version of the specification. So for example, if you have reachability to very small region, we initially solve learning for reaching a large region, and then gradually decrease the target region to be the one we are looking for. And the same thing with zeta. We start from a small zeta and then we gradually increase zeta to have it closer to 1. So now let's see how the algorithm works on the case study, so the card poll system. You don't need to look into the details of these equations. This is just the underlying equations that generates the states of the system. We just use it as a black box to generate data. And then we have the specification as a combination of safety and reachability. Again, the learning took more than 20 hours without converging. But when we used this sequence for the target range, we had convergence within 44 minutes. The network for the policy and for the value function, we use neural network with the proper number of inputs and outputs. And here are the results. So the lower bound we get from the learning is 95%. And to validate this, we ran 50,000 passes. And out of these 50,000 passes, only 515 violates the specification. And you can see here the cloud is the cloud of the position and the angle of the system. And in a small number of cases, the requirements on the position is violated, and the safety constraints on the pole is also violated in a small number of cases. And you can see here the actual probability is 98%, but the lower bound computed by the learning is 95%. And here you can see the statistics of satisfying the reachability. All the passes reach the target state, the target interval, within 150 time steps. Another example we tried was boat driving. So the boat wants to go from the left bank to the right bank to reach the port within a specific range. So the range was 95 until 105. But again, the convergence, the learning took a large amount of time to converge, but we started from a very large target range and gradually decreased the length of the target range to the intended interval to help the learning to converge. And the same thing we did with the value of zeta, starting from a smaller value and then gradually increasing it to become closer to 1. And here you can see that the satisfaction probability, the lower bound computed by the learning algorithm as a function of initial position of the boat. And by increasing the value of zeta and changing the target range properly, so we get a better lower bound for the satisfaction probability. Okay, just to summarize, discuss the policy synthesis for systems under uncertainty over continuous state spaces. We use RL to satisfy specification. We get the convergence guarantee under suitable assumption and lower bound on the optimal satisfaction probability regardless of that assumption. We also tried the specification guided learning for improving the performance of the learning in terms of time. In the future, we plan to perform policy synthesis for zero-sum games. Using data, we want to study midfield games. And also we are working on compositional methods for handling larger scale systems. Thanks for listening. I will be happy to answer if you have any questions.